Hello friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. Friends, today we are going to discuss some of the important concepts related to your electrical machines subject, and the topic name is transformer. First of all the candidates who are joining me right now, please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. And till then I am going to list out the topics that we are going to cover today. First, we will see the remaining portion of efficiency. Then we will go to autotransformer. Then we will see three-phase transformer connections. And then we will see the parallel operation of the transformer. Now, all of you who are joining me, please tell me quickly whether my audio and visual quality is okay for you so that we can proceed for the session. I'm waiting for your response. Till then, I'm moving to the next slide till you report whether my audio and visual quality is okay. This is the initiative started by Team Gradeup. As you can see on your screen, this is named as hashtag Prep Smart Stay Safe. Under this initiative, we are communicating to our students how you should wash your hands to protect yourself and others against the infections related to the novel coronavirus. Venki, Victory, how are you, beta? Please tell me whether my audio and visual quality is okay. Tell me quickly. So these are the steps. You should wash your hands under the direct tap water, apply soap, rub hands palm to palm, lather the backs of your hands, scrub between your fingers, rub the backs of the fingers on the opposing palms, clean thumbs, wash fingernail, fingertips. Then wash your hands under the direct tap water, dry it using a towel and switch off the tap by using a tissue paper or the towel. And now your hands are clean. This procedure should approximately take 20 seconds as per the government regulations. Venki Victor is saying video is not clear. You better see your internet connection because I am watching it parallelly on my mobile so that I can see your comments, and I think it is clear. The next slide on your screen shows the contact number for the control room which is being set up at the national level to address the queries related to the novel coronavirus. You may reach this number for any guidance, support and technical queries. This also we are communicating under the initiative hashtag Prep Smart Stay Safe as started by Team Gradeup. The next slide on your screen shows very important information. In this time when everybody is restricted to stay in their home, the Gradeup is offering to you free of cost classes in the Gradeup classroom. For example, M.N. Ramesh Sir, Chandan Jha Sir and Rakesh Talreja Sir, they are taking engineering services mains practice classes 9 a.m. in the morning. Chandan Jha Sir is taking concept on fingertips classes 12 p.m. I am taking engineering ethics classes for engineering services 2021. BYJU'S Sir is taking concept on fingertips classes at 2 p.m. and M.N. Ramesh Sir is taking concept on fingertips classes at 7 p.m. Good evening, Vishal Kumar. How are you? Now there is one more important information regarding this Target Gate 2021 batch. This is an electrical engineering batch that we have started. The most remarkable feature of this batch is this is the first bilingual batch started by Gradeup. It means इसमें हिंदी और इंग्लिश दोनों में बातचीत होगी so that your learning does not become limited because of your language barriers. Now let us see who are the faculties who are going to take classes in this batch. Rakesh Talreja Sir, MEIC Bangalore, AIR 9. He is having 10 plus years of experience. Myself, Ashutosh Saxena, M.Tech, IIT B.H.U, 10 plus years of experience. M.N. Ramesh Sir, ME Usmania University, Hyderabad, 17 plus years of experience. BYJU'S Sir, 19 plus years of experience. Chandan Jha Sir, M.Tech, NIT Hamirpur, 9 plus years of experience. Good evening, Rajesh. How are you? And I can tell you more than 10,000 people have started the free trial. So even if you don't go for this, at least you should go for this free trial. That is very, very important. Then you will experience how Gradeup is changing the life of thousands of students. Now there is one more important information regarding the upcoming Mega Mock Challenge schedule for the electrical aspirants. If you want, you can take the snapshot for this. SSC JE 2019-20 Paper 1 Mega Mock Challenge is going to be conducted on 9th of May. UPPSC Assistant Engineer 2020 Paper 1 is going to be conducted on 16th May. UPPSC Assistant Engineer Paper 2 is going to be conducted on 23rd of May. BYJU'S Steel Management Trainee 2020 Mega Mock Challenge is going to be conducted on 30th May. I am fine, Rakesh. Thank you for your concern. So you can take the snapshot for these upcoming Mega Mock Challenge. If you are really done with your preparation, you can appear in this, and other candidates also who are not well with their preparation, they can appear in this examination, in this test, and you can see what is where you are standing. I hope it is clear to all of you. Now we are going to start the session. But before that, let me tell you that if you want more and more these type of sessions from us, then you have to do two things which are very, very important. Number one, you have to like this video, and number two, you have to share this among your social media groups, among your colleagues, friends, classmates, whosoever is there. So two things are important. You share this video, these classes, these lectures, these sessions, and you like this page. That is very, very important. Right now I can see almost 20 plus people are there with me, but number of likes are just 10. ऐसी नाइंसाफी मत करो बेटा मेरे साथ, जल्दी से like करो. Quickly like the session. I want all of you to like the session within a count of 1, 2, 3. 1, 2, 3. All of you now go and join and like the session. Quickly like the session. Good evening, Goda. Kavya, how are you? Now let us start with this separation of hysteresis and eddy current losses. We have seen that the transformer core losses are comprising of two losses: hysteresis loss and eddy current loss. We have seen the expression for hysteresis and eddy current loss also. So you can write it like this: core losses as KH F Bm raised to the power n, where n is the Steinmetz constant for the hysteresis loss, and for eddy current loss you can write Ke F square Bm square. Is it clear? Now you see that your supply voltage or the terminal voltage is approximately equal to your induced EMF. Say this capital E, and this is equal to root 2 pi f phi and number of turns if you are considered primary or secondary windings. Now this phi is how much? This phi is nothing but V into A. So if you put it here, so this voltage you can write as, this voltage beta is going to be directly proportional to how much? Root 2 pi, they all are constant, yes or no? So V is going to be directly proportional to F into B, and area, cross-sectional area and number of turns are going to be constant. Or you can say, better write it Bm, that is the maximum value of the magnetic field density. So this is going to be directly proportional to V by F ratio. So if you keep this V by F ratio constant, so that this value of maximum magnetic field density is constant in the transformer core, then what you can write, please tell me. If this is going to be constant, so you can say this as K1 and you can say this as K2. So you can write the core losses like this: PC is going to be K1F plus K2F square. Now if you wish, then you can write it like this also, PC upon F, which is going to be K1 plus K2F. Now what is this value? This is the core losses in one cycle. Okay? Yes or no? And if you see what is this? This is hysteresis loss in one cycle, and it is a constant. And if you see this one, it reflects the eddy current losses in one cycle, and they are directly proportional to frequency. I hope it is clear to all of you. Now if you conduct different experiments, okay, for different conditions, if you plot the variation of this core losses in one cycle with respect to frequency. So what I am going to do, I am going to draw the per cycle core losses. I am going to draw the per cycle core losses. This is your frequency and this is your core losses per cycle. So you are going to get a linear equation, because if you see this expression K1 plus K2F, this is nothing but a straight line equation. I hope it is clear to all of you. Basic mathematics, you must be having this much understanding. So you are going to get a variation like something this. I hope it is clear. Now if you see, this intersect at the y-axis, this is going to give you what? This is going to give you the value of K1. What is K1? Per cycle hysteresis loss. Yes or no? Suppose you are trying to find it at a given frequency F. So this is going to be your K1. That is the hysteresis loss per cycle, and this is going to be how much? This is going to be your K2F. That is the eddy current losses per cycle. So from this variation you can easily find the value of K1 and K2. If you know the values of K1 and K2, very easily you can separate the hysteresis and eddy current losses. Yes or no? Because hysteresis losses are going to be how much? K1 multiplied by frequency, and eddy current losses are going to be K2 multiplied by F square. So if you know the values of K1 and K2 from this diagram, this plot, then you can easily find separately what are the hysteresis losses and eddy current losses. All of you, please tell me, are you comfortable with this understanding? And if you have any doubt, then you can ask me. Please tell me quickly, are you comfortable with this? And if you have any doubt, then you can ask me. Is it clear to all of you? And don't forget to do those two things. What are those two things? Number one, liking the page. Number two, sharing this video in your friends group, colleagues group, mates group. Is it okay to all of you? Now let us proceed. Now you see, if you see whatever we have seen till now for efficiency, the efficiency for a distribution transformer the efficiency calculation for a distribution transformer is termed as all day efficiency. It is also called energy efficiency also. What is the reason? The reason is the primary of the distribution transformer is always on, so that core losses are occurring every time. I hope it is clear to all of you. If you see a distribution transformer, for a distribution transformer, whether there is a load connected on the secondary side or not, the power must be available all the time in the primary side of the distribution transformer. So definitely core losses are going to occur, whether it is no load condition, full load condition, or any load condition in between no load and full load. It means if you want to know the performance of your distribution transformer in terms of efficiency, then the general expression for efficiency is not going to help you, because it is not going to give you the actual working condition or the performance of the transformer, distribution transformer. What we are going to use is, we are going to use a different expression for efficiency, which is in terms of energy, and that is why we are calling it energy efficiency or all day efficiency. Now let us see what is the formula for this. The all day efficiency, we are writing the formula as output kilowatt hour in 24 hours divided by output in kilowatt hour in 24 hours plus copper losses in 24 hours plus core losses in 24 hours. I hope it is clear to all of you. If you want, then I can give you one problem also, so that you better understand this issue of all day efficiency and energy efficiency. Just write one question and try to solve it. I am going to give you a question. A 500 kVA transformer has a maximum efficiency of 98.6% at 350 kVA unity power factor. During the day it is loaded as follows. Yes, Ranjit, beta, if no load condition is there, definitely the copper losses are almost nil or zero, you can say. So you will take accordingly. What is the problem? What is the doubt you are having? If it is on no load, so you take the copper losses for that time as zero. What is the problem? Now during the day, it is loaded as follows. 6 hours 300 kVA, 0.8 power factor lag. 4 hours, 240 kilowatt, 0.6 power factor lead. 5 hours, Ranjit, for you it is no load. For you it is on no load for 5 hours. And for 9 hours, it is 225 kVA at unity power factor. And you have to calculate the all day efficiency. Is it clear to all of you? You just note down this question. I am giving you this something as homework. You do it after this class and you give me the values. I will ask you this value tomorrow. Don't solve it today. Just take your time. I know it is a lengthy calculation. It is going to be a bit lengthy calculation. But if you do this problem correctly, then you will understand the idea behind this all day efficiency or the energy efficiency. And tomorrow, if you are not able to solve it, tomorrow I will solve it along with you. I hope it is clear to all of you. Is it okay, all of you? Please tell me. Just take a note of this as your homework and try to solve it after the class today itself, and tomorrow in the class. Before I start the class, I will ask you the answer, and if you are not able to solve it, tomorrow I am going to solve it, okay? Now let us start with this autotransformer, okay? Now you see, you all must be aware with this, the basic idea about autotransformer, that your autotransformer is a special type of transformer which is having only a single winding, okay? The most important feature is that a single winding is used instead of two windings. Instead of two windings. Yes or no? Now you forget about all the technical details. I asked you that the same advantage which I was asking you when we started the transformer. See, if you just need to step down the voltage, then you can use the potential divider, or you can use an inductive coil also. Now, why we are going for this auto transformer? What is the advantage? The advantage is that auto transformer is going to give you a step up voltage. From a small input voltage, you are going to get a larger output voltage. Because of which phenomena? The phenomena of mutual induction or the transformer action, you can say. Now, if you forget about all the details about the auto transformer, you please understand this, that instead of using two windings, you are using a single winding. If you are using a single winding, then definitely there is going to be less copper needed. If you are using single winding instead of two windings, there is going to be less copper required. So if less copper is required, definitely losses are going to be less. Yes or no? Are you getting this idea or not? In terms of copper losses, I am saying, if you are using single winding instead of two windings, definitely there is going to be saving in the copper material because you are using single winding. And if there is a saving in the copper material, so definitely there is going to be less losses in terms of copper losses, I square R losses. The second idea is, if you are using a single winding, then the leakage flux is also going to be very less. Leakage flux is also less. If leakage flux is also less because you are using a single winding, definitely core losses are going to be less. I hope you all are comfortable with this. I hope you all are comfortable with this. Now let us see some basic idea. If you are having this much understanding, then we can proceed with the autotransformer. Now suppose here you have connected the AC source. This is your AC source. This is the high voltage terminal. This is the low voltage terminal. And suppose here you are having NH. High voltage winding, high voltage terminal is accompanied with NH number of turns, and it is accompanied by NL number of turns. That is the low voltage terminal. I hope it is clear to all of you. Now you see, no. Prashanti Jignu is saying insulation required is less. That we will discuss. Don't worry about this. Ranjit Mail is asking, sir, how we can find the wire size for a transformer. Beta, you wait for the right moment. Okay. Don't try to deviate the class. What we are discussing, just focus here. Ranjit, please hold your emotions. Now, Prashantni is saying that we are going to use less insulation. Now, please understand this problem. If you are using this type of auto transformer at no load condition, if no load is connected here, then there is a possibility of very high voltage occurring on the low voltage terminal, and that may damage the insulation or the nearby personnel. So this is a disadvantage of this auto transformer. One more disadvantage. If you see an auto transformer, a part of the winding is electrically directly connected to the primary side and secondary side. So insulation requirement is going to be more comparatively better. I hope it is clear to all of you. Now just focus here. We are assuming current at the high voltage side as IH, and here we are assuming the current in the low voltage winding as IL. Now all of you don't deviate and listen to me properly, otherwise you will miss the point. VH, IH is the voltage and current at the high voltage terminal. NH is the number of turns, total number of turns at the high voltage side. NL is the number of turns at the low voltage side, and VL and IL are the voltage and current at the low voltage side. Now you tell me, if this voltage is less, then definitely you can say IL is going to be more than IH. Yes or no? Are you getting this? If this voltage is less, this voltage is more, then this current must be more than this current. Yes or no? Are you getting this? Because the KVA is going to be same. I hope you are okay with this. Now, if this current is more and in this winding the current is IH in this direction, can you tell me what is the current in this winding? What is the direction of current in this winding? Because this current is more, this current is less. So there must be some current in this direction. And what is that current? That current is going to be IL minus IH. because at this point if you apply the KVL, then you will get IH plus IL minus IH as IL. So this is how we are going to represent the current direction. Is it clear to all of you? Now let us see further. As the flux is common, then you can write VH upon NH is equal to VL upon NL. What is this? This is nothing but EMF per turn. If the same flux is going to be linked, then definitely EMF per turn is going to be same. That we have seen as per the derivation of induced EMF in the transformer case. So you can write beta as VH upon VL as NH upon NL, and this we are writing as Autotransformer turns ratio. This we are writing as Autotransformer turns ratio. Now let us see the MMF balance equation. For the MMF balance equation, we are neglecting the I naught current. Okay, that no load current component we are ignoring. So we are writing as how you are going to balance the MMF. MMF balance equation is going to give you NH minus NL. Suppose you call this part of the winding as A and this part of the winding as B and this part of the winding as C. Now we are going to compensate the MMF. How? The MMF linked with this AB part, this is going to compensate the MMF linked with this BC part. So what is the MMF linked with the AB part? What are the number of turns? Total number of turns NH minus NL. So what are the number of turns? NH minus NL. What is the current? IH. So we are writing NH minus NL into IH, and this is equal to the MMF in the BC part of the winding. What are the number of turns? Number of turns are NL. What is the current? IL minus IH. So it is going to be how much? It is going to be NL multiplied by IL minus IH. Just expand this, so you will be getting NHIH minus NLIH is equal to NLIL minus NLIH. So these two are going to be cancelled and you will get IH upon IL as NL upon NH, or you can say 1 upon A autotransformer. Is it clear to everyone? Now we want to see the saving in copper material in comparison to a two-winding transformer. We want to see what is the saving in the copper material. Now you see the copper weight, you can write as copper volume multiplied by copper density. Now density is not going to change because density is something very characteristic of a material. So we are saying that this copper weight is going to be directly proportional to volume. Now this volume you can write as cross sectional area multiplied by the conductor length. Yes or no? Now your cross sectional area is going to be directly proportional to the current. You remember this? Your current is given as current density multiplied by the cross sectional area. So if this current density is constant, then your cross sectional area is going to be directly proportional to the current. So this is going to be, cross sectional area is going to be directly proportional to current. And your conductor length is going to be directly proportional to number of turns. Why? More number of turns, more the length of the conductor. Less number of turns, less the number of conductor. So you can say that your copper weight of the conductor is going to be directly proportional to the MMF. Is it clear to all of you? How we have achieved this copper weight is directly proportional to MMF. Now we are going to compare the copper material in case of autotransformer with respect to copper material in case of a two-winding transformer. Now if you see, we want to write the total MMF. I am writing total MMF for the autotransformer. So it is going to be how much? It is going to be the MMF in AB part and MMF in BC part. You remember this? Total MMF I have to write. So I am writing like this. It is going to be NH minus NL. What is the current? It is going to be IH plus NL multiplied by IL minus IH. Now if it is a two-winding transformer where high voltage and low voltage windings are separate, you are having two separate windings for high voltage and low voltage windings. So this is going to be NHIH plus NLIL. Definitely beta Gonda Kavya, definitely. This is very important for the transformer action. MMF balance is the most important feature of the transformer action. You try to see here. If you see this ABC section of the winding, if no load is connected here, and you want to set up a flux in the winding, so you need some current. That current we are calling as the no load current. Now the moment you connect the load here, there is going to be some current coming out of this, which is the extra current in this common part of the winding, that is BC. If current is going to flow in this common part of the winding, then there is going to be some MMF. And that MMF is going to oppose the flux in the common core of the autotransformer. But I told you that in case of transformer action, flux cannot change because flux is decided by the input voltage. If you are not changing the input voltage, you cannot change the flux. So what is going to happen? Extra current is going to be drawn from the supply. And what is the purpose of that extra current? The purpose of that extra current is to balance the MMF at the secondary side. When I was doing this MMF balance equation, I was doing nothing but I was balancing the MMF for the AB part of the winding and BC part of the winding. Gonda Kavya, please tell me, are you comfortable with this? Is it okay now? Do you understand this? Please tell me quickly, are you comfortable with this? I hope it is clear to all of you. Now let us focus here. Now you must be knowing with the MMF balance we have got that NHIH is equal to NLIL. This we have got out of the MMF balance equation. So from here you can get, if you expand this, then you are going to get NHIH minus NLIH plus NLIL minus NLIH, and this is being divided by 2NHIH, because NHIH is equal to NLIL. If you see, this NHIH and NLIL are same, so I am writing here 2NHIH, and this minus NLIH and NLIH are going to be added, so this is going to be 2NLIH, and this is being divided by 2NHIH. Okay. Now if you simplify this beta, if you simplify this, then you will get the copper weight or the copper material in case of autotransformer as copper weight or material in case of two winding transformer as NH minus NL upon NH. If you simplify the previous equation, so you will get 1 minus NL upon NH. What is NL upon NH? This is going to be 1 minus 1 upon A autotransformer. Now if you want to know the saving in the copper, if you want to know the copper saving, then copper saving is going to be what? Where you are using more copper? You are using more copper in the two winding transformer. So it is going to be copper in the two winding transformer minus copper in the auto transformer divided by, with respect to what? Copper in the two winding transformer. Yes or no? If you see, this is going to be 1 minus copper in the auto transformer divided by copper in the two winding transformer, and this is going to be 1 minus, what is this ratio? This ratio we have achieved 1 minus 1 upon A auto transformer. So if you simplify this, then you will get the final relation that copper saving in an auto transformer is going to be 1 upon A auto transformer. If you want it in percentage, you multiply by 100 and you will get the percentage saving in the auto transformer instead of two winding transformer. Now you see very important point here, that please focus, all of you please focus here, very important point I am going to mention here. You must remember how we have configured this A auto transformer. Go back and check how we have defined the auto transformer turns ratio. We have defined the auto transformer turns ratio as the number of turns for the high voltage terminal and number of turns for the low voltage terminal. This is very, very important. You don't confuse. See, different books are going to use different notations. So you are getting different formulas, but you stick to one convention which likes to you, which suits to you, and you follow that only. Because if you keep on remembering lot of formulas, then you are going to be confused in the examination. This is how we are defining the auto transformer turns ratio. Now you please understand, if this A auto transformer is more than, then saving in copper material is not significant in comparison to extra cost due to insulation, etc. So the application of auto transformer is being restricted for the turns ratio less than 2. And the best application of auto transformer you will get when this turns ratio is very close to 1. Okay, when it is very close to 1, then you are having a great amount of saving in the copper material. Then it is going to be the best application of the auto transformer. Now let us see the components of power in case of autotransformer. Yes or no? If you see the low voltage side, at the low voltage terminal, what is the power? It is going to be VL multiplied by IL. Now this IL you can write as IL minus IH plus IH. Plus minus IH I am doing. If you separate it, then it is going to be VL IL minus IH plus VL IH. Now if you see this part VL IL minus IH, this we are calling as inductively transformed VA or the volt ampere, and this remaining part we are calling as conductively transformed volt ampere. Now please try to understand why we are saying so, because if you see BC part of the winding of the autotransformer, what is the associated power? VL IL minus IH. You remember that? I am saying about the BC section of the winding. For the BC section of the winding, what is the associated power? It is going to be IL minus IH multiplied by VL. If you expand this, then you are going to get VLIL minus VLIH. Yes or no? But this VLIL is going to be how much? This VLIL is equal to VHIH. This we have seen for the common flux or the voltage per turn induced in the autotransformer. Equation number 1 we have seen. So you can write this power for the BC part of the winding as VHIH minus VLIH, or you can write as VH minus VL, and IH is going to be common. Now can you tell me what is this VH minus VL multiplied by IH? What is this? If you see this VL minus VH is this much, sorry, VH minus VL. Let me write it with a different color. This is VH minus VL for this part of AB part of the winding, AB section. And what is the current? Current is IH. It means your auto transformer is nothing but a two winding transformer which is having a direct connection, electrical connection between the two windings. Because if you see this step down transformer, this is a step down transformer. For this step down transformer, this AB section and BC section of the winding, they are acting as if they are two winding transformer. One winding AB section, one winding BC section. Is it clear to all of you? Please tell me. Are you comfortable with this? Now if it is so, it means in between these two sections of the winding AB and BC, the power is being transformed because of the transformer action. And what is the method through which power is being transformed in case of a two winding transformer? That is mutual induction. So this part of the power, component of the power, we are calling as the inductively transformed power. Inductively transformed power. If you see, this is for BC section of the winding. It means your auto transformer is actually transferring power in two components. One component is inductively transformed VA, which is because of the transformer action. that is mutual induction. And the second component is the conductively transformed VA. Conductively transformed VA because of the direct connection between the primary winding and secondary winding. What is your doubt, Sanjay Bontu? Please tell me. Beta, what is your doubt? You please tell me quickly so that we can sort it out. Now, if you want to see the ratio, let us see the ratio. If you want to see the formula, the conductively transformed VA or the power with respect to the total power of the autotransformer. So this is going to be VLIH divided by VLIL. VL going to be cancelled, so you are going to get IH upon IL, and this is going to be equal to NL upon NH, which is nothing but 1 upon A auto transformer turns ratio, and that is nothing but copper saving. I hope you remember that. And what is going to be inductively transformed power and the total power? This is going to be 1 minus 1 upon A auto transformer. So these two equations you can use, but you have to remember that auto transformer turns ratio we are defining as high voltage terminal number of turns with respect to low voltage number of turns. Tripurtipati Naveen is saying, Beta, you can go to the Gradeup app. Let me tell you, you go to the Gradeup app, you see the exact schedule of the classes being planned. Gradeup is offering to you lot of classes daily. I hope it is clear to all of you. These electrical machines classes we are running Monday to Saturday, 8:30 p.m. evening. And if you have missed my lectures, you can go to the Gradeup playlist and you can see the rest of the lectures. I hope it is clear to all of you. Now, I am going to give you one problem so that you better understand this auto transformer issue. A 25 kVA, all of you focus here, a 25 kVA, 2500, 250 volts, 2 winding transformer, to be connected as an auto transformer. Okay, determine the voltage ratio and the kVA rating as auto transformer for all possible connections. If you are not able to see my writing, if there is any problem, then you can ask me if you have any confusion anywhere. If you have any problem in reading the text on the screen, I am going to read out to you so that you understand it better. I am again reading this so that you can note down the question. The question is, a 25 kVA, 2500/250 volts, 2 winding transformer to be reconnected as an auto transformer. Determine the voltage ratio and the kVA rating as auto transformer for all the possible connections. Is it clear to all of you? Is it clear to all of you? And this is your diagram. Your diagram for the 2 winding transformer, given 2 winding transformer is something like this. This terminal voltage is 2500. Current is 10 ampere. You can find it? Yes or no? You can find it from the kVA rating and the respective voltage. You can find the rated current. So if you divide 25 kVA by 2500, you will get 10 ampere. And if you see this winding is low voltage winding. निशंकर साहू is saying good night. बेटा अभी good night नहीं हुआ है, थोड़ा सा और पढ़ना है, उसके बाद good night होगा. Okay, निशंकर साहू, just wait for the while. This is 250 volts. If you want to find the current, divide this 25 kVA divided by 250 and you will get the current as 100 amperes. And these are the dots. Current entering, current leaving. Is it clear to all of you? This is AB, that is the primary side. I am writing AB, and this side I am writing as CD. Yes or no? Now let us see one by one different cases we want to see. The first connection that we want to see is under additive polarity. Now please try to understand, whenever you are having two inductive coils, for example for a two winding transformer you are having two inductive coils, one for the primary side, one for the secondary side. Now you are reconnecting those windings to form an autotransformer. Now there are different ways in which you can reconnect the windings. You have to consider the two cases. What are those two cases? Number one, with the additive polarity. Number two, with the subtractive polarity. So we'll see first the additive polarity. If you are following the additive polarity, beta, if you are following the additive polarity, see what is going to happen. Suppose this is your AB section, sorry, CD section, and this is your, this is dot, this is dot. I am saying this is your CD section and this is your AB section. Just go to the previous figure and see. What is AB section? High voltage side, high voltage winding, this is low voltage winding. Okay, so what I am going to do, I am going to take this winding and connect it here. Electrical connection. So I am getting this. Now whenever you are reconnecting the two winding transformer as an auto transformer, one thing you have to see, and that is the current sense must be same. You have to keep the current sense must be same. Current sense in the windings must be same. What is the meaning of this? The meaning of this is, if you see this low voltage side, at the low voltage side, this 100 ampere current is going from no dot to dot. It is going from this part, D part I am calling as no dot, and this part I am calling as dot. So for this low voltage winding, the current is going to travel from no dot to dot, and it is 100 amperes. Yes or no? So for this winding, the current must be no dot to dot, and it is going to be 100 amperes. Now if you go back and see the high voltage winding, in the high voltage winding, the current is from dot to no dot, and the magnitude is 10 ampere. So again I am writing it here, dot to no dot and 10 ampere. Is it clear to all of you? This is how we are putting the additive polarity. Wherever you put the dot, we are assuming that the dot terminal is acting like a positive terminal. So for the additive polarity, you have to connect them with the same polarity. Positive, negative, so that their EMF is added. I hope it is clear to all of you. Now I am going to connect the source and load. And it is very important, you better see, this is very, very important. If you miss this, then it is going to be little difficult for you to understand. Suppose I am going to have this terminal. Now here 100 ampere going, here 10 ampere going. So there must be 110 ampere coming to this node. It means you can connect the source here. You can connect the source here, because you have to feed the 110 ampere, and where you are going to connect the load? You are going to connect the load here. Now what is this voltage? This voltage is the high voltage side voltage. What is the high voltage side voltage? It is 2500. And what is this voltage? This voltage is how much? 250 volts. But because this is additive polarity, for the additive polarity, what is the total voltage you are getting at this side? This voltage plus this voltage. So you are getting 2750 volts. And what is the current here? It is going to be 100 amperes. Yes or no? If it is 100 amperes here, so it is going to be 100 amperes here. If it is 110 amperes here, so it is going to be 110 amperes here. All of you, please tell me, can you follow this reconnection of auto transformer from a two-winding transformer to auto transformer? Are you able to follow this? Subramaniam Suresh, you are right. All of you tell me, can you follow this reconnection of the two-winding transformer into the auto transformer with the additive polarity? Are you able to follow? And if you can follow this, you can directly write the auto transformer turns ratio. Yes or no? This is going to be how much? You remember that? This is going to be high voltage terminal to low voltage terminal. You remember this? I think it must be clear to you. So if this is VH upon VL, what is VH? VH is going to be 2750. What is VL? VL is going to be 2500. If you solve this, then you are going to get 1.1. And if this auto transformer turns ratio is close to 1, then beta you are getting the best performance for the auto transformer. Now let us see what is the kVA rating in terms of auto transformer. You can find it from any side. Either you find it from the load side or you find it from the supply side. It has to be same, because power is not going to change. So you can find it from the load side. Load side voltage 2750, load side current is 100. Or you can find it from the source side. It is going to be 2500 multiplied by 110. So you are going to get as 275 kVA. Yes, you are right. Now you see, this is the total kVA of the auto transformer. Can you tell me what is the conductively transformed VA and what is the inductively transformed VA? See, when this transformer was used as a two-winding transformer, what were the kVA rating? The kVA rating was 25 kVA. So inductively transformed VA is going to be 25 kVA, and the rest is going to be how much? Rest is going to be the conductively transformed kVA, so that the total is 275 kVA. I hope it is clear to all of you. All of you, please tell me, are you comfortable with this? How to find out the conductive and inductive kVA? If you want to find it separately, you can find it separately also. You will get the same result. Or you can use directly your brain also. Whenever you are, because I have already told you that your auto transformer is nothing but a two-winding transformer. What are the two windings? This winding CD and this winding AB. So these are the two windings of the two-winding transformer previously. So the transformed VA, inductively transformed VA, is nothing but the rating of the previous two-winding transformer, that is 25 kVA. Directly you can observe it. I hope it is clear to all of you. Now we are going to see Now we are going to see the second connection in case of additive polarity. This was the first case or the first connection for the additive polarity. Let us see the second case. The second case for the additive polarity we are going to see, and it is going to be how it is going to be. Now with the additive polarity, this is CD part of the winding and this is going to be AB part of the winding. Because it is additive polarity, so it is going to be same. And here we have seen for the CD part of the winding, what is the current direction? Just go to the previous figure. What is the current direction in the CD part? It is no dot to dot 100 amperes. No dot to dot 100 amperes. So this is going to be no dot to dot 100 amperes. And if you see this high voltage side, what is the current? Dot to no dot 10 ampere. So it is going to be dot to no dot 10 ampere. Again I am taking out this terminal. 100 ampere here going, 10 ampere here going. What is the total current? Total current is going to be 110 ampere. In the previous case, I have supplied this current from this side by connecting a source. But if I connect a load here, then also I can have this much current. So what is the current here? The current here is going to be 110 ampere and this is going to be your load. And where you are going to connect the source? Because 100 ampere here, 110 ampere here, so there must be 10 ampere from here. Yes or no? You must satisfy the KCL and KVL. And if it is 10 ampere here, so it is 10 ampere here. So this is going to be your source side now. This is your source side. What is the voltage here? Can you tell me what is the voltage here? It is going to be 2750 volts. Because this is how much? This is 2500 volts. And this is how much? This is 250 volts. You just add them with the additive polarity and you are getting 2750. What is the voltage here? The voltage here is going to be 250 volts. Now you have this connection. Vasishta Muthi Reddy is asking, sir, why not take root 3 for VI for... Beta, we are talking about a single phase transformer. It is not a three phase transformer. It is a single phase transformer we are talking about. Don't get confused. If it is not mentioned in the question, take it as a single phase transformer. That is why we are not taking the factor of root 3. Is it clear to all of you? Now for this second connection, just focus very keenly, just see this. What is going to be the A autotransformer? What is the autotransformer turns ratio? High voltage side upon low voltage side. High voltage side is 2750. Low voltage side 250. What is the autotransformer turns ratio? This is going to be approximately 11, you can say. Just check it. I think it is going to be 11. Now if this is your autotransformer turns ratio, then this is not a good option. We are calling this as the bad option. This is not a good option to reconnect the autotransformer. Yes, Gonda Kabe, you are right. It is going to be 11. Now let us try to find the kVA rating of the autotransformer. The kVA rating of the autotransformer either from high voltage side or low voltage side. High voltage side, it is going to be 2750 multiplied by current. What is current? Current is 10 ampere. Go to the low voltage side. What is the voltage? The voltage is 250. What is the current? Current is 110. Same value you are getting, that is 27.5 kVA. I hope you are getting this. Now let us see the next connection. Just we'll see it later. Just first you focus here. Now we are going to see the second case with the subtractive polarity. For the subtractive polarity, what you are going to do? We are going to reverse one of the winding at a time. We are going to reverse one of the winding at a time. Suppose this is not, this is AB, this is we are taking as AB, and this is we are taking as CD reverse. We have reversed the CD winding. I hope it is clear to all of you. Now this is going to be the subtractive polarity. But current sense is not going to change. Whenever you are going to reconnect any two winding transformer as autotransformer, you must remember this fundamental principle that the current sense in the winding is not going to be changed. That is very, very important. So you go back to the previous diagram. For the CD section, the 100 ampere is flowing from no dot to dot. So 100 ampere is flowing from no dot to dot. Is it clear to all of you? No dot to dot, 100 amperes. Again, if you see, for the high voltage side, 10 ampere is flowing from dot to no dot. 10 ampere is flowing from dot to no dot. So beta 10 ampere is flowing from dot to no dot. Again, I am going to take this terminal. 100 ampere coming, 10 ampere going. How much coming in this terminal? 90 ampere. If 90 ampere is coming like this, then very easily you can connect a load here. Yes or no? 90 ampere coming here, 90 ampere going here, and here we are going to connect the source. Suppose source is connected here. Yes or no? Now if this is 100 ampere, so this is going to be 100 amperes, and 10 ampere here, 90 ampere here, so it is going to be 100 amperes here. Now this voltage we are saying AB section as 2500 volts, and this voltage with the reverse polarity is going to be minus 250 volts. That is the meaning of subtractive polarity. So what is the total voltage here? You are getting 2500 minus 250. So it is going to be 2250 volts. Now this is your final reconnection. This is load. Now can you tell me the auto transformer turns ratio, high voltage upon low voltage? What is high voltage? 2250. What is low voltage? What is the low voltage here? 2500 volts. So this is going to be 2500 volts. What is the turns ratio you are getting? Sorry, just reverse it. I have done it low voltage upon high voltage. Just reverse it and write it as high voltage upon low voltage. So this is going to be 2500. This is the high voltage, and the low voltage is 2250. If you simplify this, then again you are going to get some value as this. So you are getting very close to one auto transformer turns ratio. So it is going to be a good option, you can say. Is it clear? Now again, if you want to see the kVA rating of the auto transformer, then you can either find it from the low voltage side or the high voltage side. It is going to be same. So if you are finding it from the high voltage side, this much low voltage side, it is going to be 2250 multiplied by 100. So you are going to get 225 kVA. Now obviously directly you can say the inductively transformed VA is going to be 25 kVA, and the conductively transformed kVA is going to be 200 kVA. Is it clear to all of you? Now if you see, just focus here, just ignore this image for a time. We are going to discuss it in the yesterday class. Just focus here. Now we are going to do the second possible connection. Let us do it on the different page. Sanjay Bontu is saying, sir, in the problem, the source is 2500. Beta, listen. We are not changing the source. Listen to me very properly. We are not changing the source. We are just reconnecting the two winding transformer as an auto transformer, and we are trying to see the different possibilities. We are not changing that voltage source into any other source. If I am connecting a different source, so I am definitely using a different source. I hope beta you understand this. Now let us see the second case for the subtractive polarity. The second case for the subtractive polarity I am drawing like this. Suppose this is your CD section, that is reversed, and this is your AB section. Again, what is the current direction for the CD section? Okay, you just do it yourself. I am going to give you this subtractive polarity as homework. This second part, because we have discussed three cases we have discussed. Better you discuss it on your own and you come to the class tomorrow, and tomorrow we are going to discuss all of them. So friends, now I am going to stop here because we are running short of time. I was supposed to discuss the parallel operation of the transformer also, but I hope that we are going to do tomorrow. Tomorrow we are going to take up the parallel operation of the transformer along with the topic for the tomorrow's discussion, that is magnetizing current phenomena in the transformer. Is it clear to all of you? Just try to revise whatever we have discussed in the today's class, and tomorrow just do two part of your homework. You are having one question I have given you for the all day efficiency, and the second is that fourth case for the auto transformer reconnection. For this problem you do it. Vishwanathan beta, we'll continue tomorrow, don't worry. Whatever the remaining part of this auto transformer we are having, that we will continue tomorrow, don't worry. Okay, Vishwanathan Murli, don't worry, we are going to cover it tomorrow. I think it is going to be cleared by tomorrow when we are going to discuss the remaining part of the auto transformer. You just wait for tomorrow. Don't forget to join me tomorrow same time 8:30 p.m. on the Gradeup platform, and we are going to discuss the remaining portion along with this parallel operation of the transformer and magnetizing current phenomena. Is it clear to all of you? Please tell me yes or no in the comment section. We are going to conclude the class beta, and some important information I want to give you, that these are the 60 plus Gradeup students in the top 100 ranks in the GATE 2020 examination. If you want, then you can be here. Sanjay Bontu beta, your doubt is not proper doubt. No. Listen to me. Suppose I remove that source. From that, then you are happy. I am not saying that I am going to change the source. I am just trying to see the different possibility. If you reconnect the two windings of the transformer as auto transformer, I want to see the different possibilities. Why you are going in that direction? I will bring you one more source. Suppose no source is connected. I am just telling you that this is the voltage, this is the current. Now reconnect it. That is the idea beta. Is it clear to all of you? Sanjay Bontu, don't lose your heart. Tomorrow we are going to discuss the remaining part, and I think you are getting, this is not I think this doubt you are getting, I don't know why. Don't try to stick to things. Just have that flexibility in your mind that we are not focusing on the changing the source beta. Suppose source is not there. I hope it is clear to all of you. Now I'm going to conclude this session, beta, and we are going to continue in the tomorrow's class 8:30 p.m. in the evening. Don't forget to join me on the Gradeup platform. And if you have any suggestion so that I can improve upon my lectures, so that you benefit more out of my lectures, then your suggestions are most welcome. You can give your suggestions in the comment section, or you can go to the Gradeup app, and in the doubt section you can mention my name and you can tell your exact doubt or any suggestion if you have for improvisation in the classes. Then it definitely we are going to take it up. Thank you so much for your time. I wish you all the best, and friends, stay safe, stay in your home, follow the government regulations, but your preparation must go on. That is the agenda of Gradeup. Prep smart, score better, go Gradeup. Thank you so much.